Chapter 12 is about matrices, and it's more than just using row reducing to solve systems of equations like we did in the beginning of the year. We're going way deeper into matrices here. Next year in pre-calculus or in college, you may actually take a class that is entirely on matrices. Or in pre-calculus, you might do another chapter that is entirely on matrices, but it's basically going to be almost a repeat of what we're doing here. So in the first section, we're going to learn how to add and subtract matrices. We have not done that yet in this class. We've done row reducing. That's it. Matrices are not a new concept to you. You've been using them in most of your classes actually for several years, and whether you know it or not, you have been using matrices every day in the technology that you use, that you probably have on you somewhere, in your back pocket, or sitting on your lap, pretending that I can't see it, or under the chair, or in your hoodie pocket, or up your sleeve, or in your hood, or under your book. What am I talking about? Your cell phone. Cell phone technology uses matrices. Your video games use matrices. Without matrices, none of those would be possible. We would not have cell phones. You would not be able to text. You would not be able to take a picture on your phone. You certainly wouldn't be able to text that picture to anybody, or Snapchat it to anybody, or face space it to anybody, or put it on the Twitters, or anything else. You would not be able to do anything that you absorb yourself with these days without matrices. There is an entire branch of mathematics. There are people who spend their entire careers making lots of money working with matrices. So if you really like this chapter, maybe that's a career that you could pursue. 6 figures, easily. So any data table is actually a matrix. You just got done with working on a spreadsheet. What you were creating was a bunch of matrices, whether you knew it or not. In this case, we have resistors in series, blah, 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 some sort of science class. We've got a bunch of trials here. We've got a bunch of different things that we're recording. And what we're creating here is a matrix. So let's get right into it. The parts of a matrix. I think we've talked about this before, but it's good to review in case we haven't. First of all, we have a bunch of different elements in a matrix. The elements of a matrix are each individual part of a matrix. So an individual part of a matrix. The elements are all of those numbers that you see in the matrix. The matrix that we're looking at is called matrix A. That's its name. A capital letter is used to call out a matrix. In the matrix, we have all of these numbers. Each one of these numbers individually is called an element. So this 5 right here, that's an element. That 7 right there, that's an element. This 4 over here, also an element. Each individual one is an element. The elements of the periodic table are called elements because they are individual things, unlike anything else. The dimensions of a matrix are m by n. M by n. M comes before n, so that should be easy to remember. But the question is, what does m represent and what does n represent? Well, m is the number of rows, and n is the number of columns. So basically you count the number of rows. This is the number of rows. That's m. How many rows are there? 3. The number of columns, n. How many columns do we have? So 4 columns, which makes this a 3 by 4 matrix. Everything that we do in this chapter that involves matrices goes row first, then column. So just remember that, row, then column, okay? In everything that we do. It's going to become important later on when we get into multiplying matrices, which you'll have to do by hand, row by column. Row first, then column. So each one of these elements has a name. If the name of my matrix is capital A, then each element is called little a. and then you call it with a subscript which position it's in. So we are in the top row and the first column, the first row and the first column. That's why this guy right here is called A1, 1. The first row, the first column. Now this guy is in row 2, still in the first column. So it's little a, 2, 1 for row 2, column 1. And then this guy is now in the third row, still in the first column. So that's A3, 1. If I move over to the second column, this is actually wrong. No. It should be 1, 2, yeah. We are in the first row, so we should see a 1, and we're in the second column, so we should see a 2. So it's 1, 2, and the one below that should be little a what? 2, 2, row 2, column 2, and the one below that should be little a what? 3, 2. And if I had another column next to that, at the top we would have a what? 1, 3, and then below that a 2, 3, and then below that a 3, 3. Remember, it goes row, then column. Okay, row first, then column always. Whether you're talking about dimensions or whether you're talking about labeling these elements. Row, then column. Couple examples, use the matrix. Now I'm calling it matrix B, capital B. This is matrix B right here. To answer the following questions, what are the dimensions of this matrix? 2 by 3. There are 2 rows and 3 columns, so it's a 2 by 3 matrix. Now let's find the value of these 4 elements here. We have B22. What is B22? It is -5. B22 means row 2, column 2, and that makes -5 right there. What is B13? We have row 1, column 3. That's that guy right there, 0. What is B21? B21 is row 2, column 1, that's 8. And what about B32? There is no 3, 2. That would mean row 3, but there's only 2 rows. So this is undefined. Okay, go ahead and try A and B for that matrix W. What are the dimensions of W? 5 by 4. What's the value of W34? W34, row 3, column 4, puts me at 9. And how about W52? W52 gives me row 5, and then column 2 is right there, and that is a 1. So that's it. We're going to hit some vocabulary here. These are things that you need to know what they are and know how to use them when they come across them. In this chapter, we are going to see all of these things over and over again. So try to use the vocabulary when they show up. A row matrix is called a row matrix because it is a matrix with only one what? Row. For example, maybe I have the matrix D equals 0, 3, 8, 1. Notice that we have only one row. There's 4 columns, but there's only one row. That's a row matrix. A column matrix, then, is probably what? A matrix with 1 column, that's right. Okay, so an example of that, maybe I have matrix E equals, and I just have 1 column, 3, 4, 5. How many rows are there in that column matrix? There's 3 rows, but it's only 1 column, and that's why it's a column matrix. With that in mind, what would a square matrix possibly be? A matrix with the same amount of rows and columns, yeah. So I'll write a matrix with the same number of rows and columns. So that would be like 2 by 2, 3 by 3, 10 by 10, and so on. I'll give you an example of that. I have matrix A equals 2, 3, 4, 5 maybe. And then that would be a square matrix. Or I could have matrix B equals 1, 2, 3, 4, 5, 6, 7, -1, 9. Just to bother you, I made it a -1. Both of these are square matrices. This is a 2 by 2. This one is a 3 by 3. That makes it a square matrix. They both have the same number of rows and columns. A zero matrix is not a matrix with no rows or columns. That's nothing. A zero matrix is a matrix with all elements equal to 0. So maybe I have a matrix like this. It's a 3 by 3 matrix, and every single element in here is a 0. Now you might say, well, what's the point? There is a use for a zero matrix. There are actually many uses for zero matrices, and they do come up. So you just got to know that it's called a zero matrix, and it just means that every single element in that matrix is 0. Does a zero matrix have to be a square matrix? No, it doesn't. I could make a column matrix, and every element in that column matrix is 0. What about equal matrices? What do you think? All the numbers in the corresponding positions are exactly the same, and the two matrices have the same dimensions. So, matrices with the same dimensions and matching corresponding elements. It's actually a pretty good definition that I just came up with off the top of my head, but it is absolutely correct. So if I have matrix capital M equals 2, 4, 6, 8, it's a 2 by 2 matrix, then capital N, in order for that matrix to be an equal matrix, would also have to be a 2 by 2 matrix, first of all, and second, the corresponding elements would have to all agree, which means if this is a 2 in that first position, M1, 1, then N1, would also have to be a 2. M1, 2 is a 4, so N1, 2 would have to be a 4. M2, 1 is a 6, so N2, 1 has to be a 6. And M2, 2 is an 8, so therefore N2, 2 must be an 8. That's what an equal matrix is. Same dimensions and exactly the same elements in exactly the same positions between those two matrices. So this is an example of how you can set up a matrix given a bunch of data. So basically, like, think about you're about to enter this into Excel and you want to organize it in a way that makes sense. So we have 5 people, Joey, Deshaun, Dario, Leo, and Alex. And each one of these guys has a bunch of statistic-looking things that they're dealing with. What sport are we talking about, probably? Football. How do you know it's football? Yeah, we have TDs. What position is this person playing? It's running back. Attempts is a stat that are kept by running backs. Yards, that'd be yards per carry. This would be yards per carry here. This is total yards for like the season or something. And then the total number of touchdowns that this person had. So we want to make a matrix. You can organize this matrix however you want. I've seen it many different ways every single year that I do this, every single class that I do it. How do you want to do it? Well, we're going to write it out by hand. So what is the easiest sounding way to do it?
Joey, Deshaun, Dario, Leo, and Alex.
Okay. Oh, you want to do that across the top? Okay, that's fine. You guys agree? Because we could also put them down the side. Across the top? So we have Joey, Deshaun, Dario, Leo, Alex. Now what?
Put games, attempts, yards, average.
Games, attempts, ATT, yards, YDS, average, AVG, and TDs. And then what? Just fill it in, yeah. All you're doing is making a matrix here. We have 11 games for Dario, 72 attempts, 439 yards, 6.1 average, and 8 touchdowns. And then just fill in the rest. So because of the way that this one's written out with the names across the top, I'm going to change these questions on the bottom. It says add all the elements in columns. I'm going to change that to rows. And then with adding the elements in rows, I'm going to change that to columns. It's okay that we did it the way that we did it. We just need to modify those questions at the bottom to match what we have for our matrix. All right, add all the elements in rows 2 and 3. What do these results mean? So row 2 is going to be, this is not, by the way, considered row 1. This is like your titles for the columns, and this is your titles for the rows. So row 1 is here. They want me to add all the elements in rows 2 and 3. So that's going to be the row here, and then row 3 is this one here. If I add all those together, what does that mean? What does that answer mean? Total what? Total number of attempts for what? For all the players, yeah. So like this team has 5 running backs. Most teams, most full-size teams probably have about 5 running backs. So if I add up all of the attempts, what I'm doing is finding out how many times during games this team rushed the football. How many times a running back carried the ball, okay? What about if I add up all of the elements in row 3? What would that tell me? How many yards all the running backs carried together over the course of the season in every football game, okay? So does that have meaning? Like, would a team want to know that? Yeah, probably. So that's the answer for the first one. Now, would adding the elements in columns 2 and 3 provide meaningful data? So column 2 is right here. I would add all those numbers together. If I added all the numbers together in column 3, I would have 2 results. Would that give me any meaningful data? No? Why not? Yeah, it's just a bunch of numbers. And notice that this is 9 games, 143 attempts, 1024 yards. Each one of these has its own unit. And you can't really add apples and oranges together. It doesn't make any sense. These are different things. Adding different things doesn't make sense. Adding the same thing does make sense. So when you make a matrix, you want to make sure that what you're adding together, if you're adding stuff together, actually makes sense. Okay? Okay, something new now. For a matrix addition or subtraction, what do you think maybe the most important thing on this page is? No, actually the word of right here, that's definitely the most important. No, of course, matrices must have the same dimensions in order for you to add or subtract them. They have to. 2 by 2 plus a 2 by 2, a 3 by 3 plus a 3 by 3, an 8 by 1 plus an 8 by 1. They have to have matching dimensions before you can add or subtract. So in this case, notice I have A, B, C, D plus E, F, G, H. They have the same dimensions. These are what? 2 by 2. Good. And notice that when we add a 2 by 2 plus a 2 by 2, we wind up with a 2 by 2. This is showing me addition. I take A plus E. It's like if I take this matrix and I pick it up and I set it down on top of this matrix, the A would be on top of the E, the B would be on top of the F, the C would be on top of the G, the D would be on top of the H. The corresponding elements add. So A plus E, whatever that is, it gets written right there. That's only one element, because I'm going to actually add those numbers together. The B and the F add together to give me whatever that number is. The C and the G add together to give me whatever that is, and the D and the H add together to give me that. This is also a 2 by 2 matrix. And the same thing is true for subtraction. Corresponding elements in this case are going to just subtract. So A minus E goes there, B minus F goes there, C minus G goes there, D minus H goes there. 2 by 2, 2 by 2, 2 by 2. 3 by 3, 3 by 3, answer will be 3 by 3. The dimensions will stay the same. It's true for any dimensions. So, let's find each of these. We are going to add and subtract matrices. First of all, check to see if they have the same dimensions. In that first one, do they? Yes. So, I'm going to wind up with what dimensions for my answer? 2 by 2. So I'm going to make a matrix that's 2 by 2, and I'm going to fill in those elements. Corresponding elements subtract. So we have negative 3 minus negative 4. Tricky. 1. Negative 3 minus negative 4. Keep, change. Negative 3 plus 4. 1. Moving across to here, we have 4 minus 12. Negative 8. Down to row 2, first column, we have 9 minus 8. 1. And then we have, in the last position, negative 5 minus negative 7, positive 2. So you'll have to be careful with your subtraction when you do it in your head. The second one, what should we do? So this one, make a 2 by 3. We have a 2 by 3 plus a 2 by 3, so those can actually be added together. And let's go across the top row. What do we get? Bottom row? 1, 2, good. You're just adding corresponding elements. Piece of cake. Okay, go ahead and do those second two. So on the second one, or third one, I guess, what do we get? A 3 by 3. And let's go across the rows. Negative 5. Negative 1. And 3 minus 4 is negative 1. Second row. That is 7. 4 minus negative 3 turns into 4 plus 3. It's 7. 5 minus negative 7 turns into 5 plus 7. It's 12. 6 minus 2 is 4. And the bottom row. 7 minus 5 is 2. Yeah, 8 minus 0 is still 8. And then 9 minus 1 is 8. So that would be your answer for those matrices. And how about that fourth one? They do not have the same dimensions, which means we cannot add these together, which means that this addition problem is not possible. You must have matching dimensions before you can add or subtract. Now the calculator will do this. This is Algebra 1 that we're looking at. On the calculator, you can bring up your template for a matrix, and if you wanted to find your dimensions, then you need the 3 by 3 matrix, and it will ask you how many rows and how many columns do you want. Now you know which are rows and which are columns, so let's do this first problem over here, this one right here. Well, let's make a 2 by 2 matrix. Okay? And then you just enter in those values. Negative 3, over to 4, down to 9, over to negative 5. get outside of the matrix, you can type minus, and then you can go back to your template. Since we're doing a 2 by 2, there actually is a 2 by 2 matrix sitting right there. So I'll click on that, and then I don't have to go through changing the number of rows and columns. And then I need -4 and 12 and 8 and -7. I've entered the problem exactly how I see it. Press enter, and there's my answer. 1, -8, 1, 2. So you can do addition and subtraction with your calculator involving matrices in that way. So let's move on. A matrix equation is an equation in which the variable is a matrix. You can use the addition and subtraction properties of equality to solve a matrix equation. So I want to find out what A is. Capital A is what? It's a matrix, yeah. We call our matrices capital letters. So when I see that capital letter sitting there, my answer should be a matrix. And this just said I can use the addition and subtraction properties of equality to get capital A here by itself. So if I want this matrix here to disappear so that A is by itself, what do I need to do to it? Subtract it from both sides. Yep. So we're going to subtract here, and we're going to subtract here. So technically I have 0, 1, 0, 12, 3, 5, 9, 7, 8, -2. And here I have exactly the same thing. I'm subtracting 1, 0, 12, 3, 5, 9, 7, 8, -2. That's going to leave me with A on the left equals, and now all I have to do is this subtraction here on the right. So while you struggle with typing that into your calculator, because this is simple, I'm just going to do it right now without using the calculator. 8 minus 1 is 7, 11 minus 0 is 11, 9 minus 12 is -3, -5 minus 3 is -8, 5 minus 5 is 0, 2 minus 9 is -7, 10 minus 7 is 3, 7 minus 8 is -1, 8 minus -2 is +10. There's your answer. Don't take the time to enter it into your calculator. It's going to take forever. Just do it like that. It's faster. But I guess if you don't trust your math, then use the calculator. Or if you want to check your work. Or if you want to make sure you got the numbers right. A couple more ideas here. If you add a zero matrix, we know what a zero matrix is. What is a zero matrix? Everything's zero. Every element is 0. To another matrix, nothing changes. But again, they still have to have the same dimensions before you can do that. Zero matrices are called additive identity matrices. The reason they're called additive identity is because anytime you add 0 to something, nothing changes. You get exactly the same thing back. That is an identity. And because we added, it's an additive identity. Additive identity matrices, zero matrices, are usually named 0, or not 0, sorry, O. The letter O is reserved for zero matrices. You might also see O with a subscript here. What are these? What's the subscript telling you? The dimensions. Yeah, the dimensions of the matrix. So you might see O with like 3 by 4, telling you that it's a zero matrix with dimensions 3 by 4. Okay? But the letter O is reserved for zero matrices. The opposite of a matrix A is negative A. Just like the opposite of 3 is negative 3. If you add these matrices together, you get a zero matrix, because 3 plus negative 3 is 0. Opposite matrices are called additive inverse matrices. Anytime you add the additive inverse to something, you get 0. So that's why it's called additive inverse. So for example, what kind of situation do we have here? Yep, we're adding a zero matrix to a regular matrix, which is means we're going to wind up with what? The exact same thing we started off with. Notice the dimensions are the same. The answer here is the exact same original matrix. What's going on in B? Yep, we have inverse matrices here, or additive inverse matrices. These two are completely the opposite of each other. We're going to get all zeros. So it's still a 2 by 2. We have 2 plus negative 2, which is 0. 8 plus negative 8, which is 0. negative 3 plus 3, which is 0, and 0 plus 0, which of course is 0. So you wind up with an answer that is a 0 matrix. Okay, we have a couple of properties to finish off the section with. Some properties of real numbers are also true for matrices. So these two properties here, the commutative property of addition and the associative property of addition, all are still true for matrices. The commutative property of addition says like 2 plus 3 is the same as 3 plus 2. You can interchange things. You can write your addition problem in any order you want. The same thing is true for matrices. Matrix A plus matrix B is the same as matrix B plus matrix A. They have to have the same dimensions anyway, and then you're just adding those elements as it is. So that's why the commutative property of addition works for matrices. The associative property of addition, notice the difference here. We have several things that we're adding together, and here the parentheses are forcing me to add A plus B first, and then I can add matrix C. The parentheses move, the grouping symbols have moved, so now I'm forced to add B plus C first, and then I can add matrix A on top of that. Notice that the letters stayed in the same position each time. This is the associative property. Grouping symbols moved, forcing me to have to add together two things before I added together the other thing. That's the associative property, and it also works for matrices. And equal matrices have equal parts. You can use this idea to find unknown values in matrices. Because these matrices are equal, then that means that each corresponding part must be exactly the same. And here in that first position, we do see a 9 and a 9. In this last position, we do see a 10 and a 10. But here we see 3x plus 1, and here we see 16. Well, this element must be the same as this element if these two matrices are going to be equal. So I can write 3x plus 1 equals 16. Subtract 1 from both sides, 3x equals 15, and then divide both sides by 3, x equals 5. So now you can solve for x using equal matrices. We can do the same thing with that other element that we haven't talked about yet, 2y minus 1 there, and negative 5 there. How would I solve for y? Okay. And we're right back in Algebra 1. Y equals negative 2. So you're using this idea that equal matrices have equal parts. This thing right here is exactly the same as this right here, and that's why I can write that equation down. That's everything I have for you for this section. So section 1, lots of vocabulary, lots of introductory stuff, and matrix addition and subtraction.